Good morning, dear students. This session we will talk about continuous beams with overhangs will be solved by kanis method. So let us see the possible changes in the procedure first. Then we will go for an example. So unlike the hinge end, we will have the same similar changes here also. So if you have a overhang portion in a continuous beam, so consider this diagram ABC, where BC is a cantilever portion or overhanging portion. So for example, if you have from the step 1, find fixed end moments like MFAB, MFBA. Now, how about changes in the procedure in this case? So moment at B shall be made 0. Okay, so which means you will have some cantilever moment MBC value depending on the load on the cantilever. So you'll have some value. For example, say if you have minus 20, just an example. So from fixed moments of portion AB, the span AB will have some MF AB value. Say, for example, is minus 30. MFBA value so plus 30. I'm just taking some random values. So you have two moments at B. So this is cantilever moment and this is from the fixity of the span AB. So if you want to make this condition like moment at B shall be 0, you see it is minus 20 plus 30. So there is a balance of plus 10. So to make sigma m be 0, I shall add minus 10 there. Then I'll get 0. So this minus 10 shall be added to make it minus 20. So cantilever moment is always fixed. So what you shall do, that this minus 10 shall be shared 0 here and 1 as share of minus 10. So which means MFBA will be modified. So for a value of plus 30, you are going to add minus 10. So that makes this plus 20 and MBC minus 20 total together is 0. So once you change this value by making it minus 10, which is equal to plus 20, this is modified moment. Okay. Now this minus 10 that is applied at B shall be carried to the far end, which is A, as half of the value. So which means minus 5 will be developed at A. So finally minus 35 is the moment at A, which is modified value. So now instead of 30 and instead of plus 30 here, we are going to use minus 35 plus 20. So that is what this means, that carryover moment, modified moment at A, modified moment at B, all these, this is what we are going to perform. And similarly, the step 2 will have a change of stiffness value. where the B, though it looks continuous, we will be treating this as a end hinge. Hence, the stiffness value will be modified to 3 EI by L. Okay, so these are the changes if you have overhanging portion. Okay, so moment at B shall be made 0 by modifying fixed end moment at B, which shall be balancing the cantilever moment value, and whatever is a moment added at B to make it 0, that value shall be taken to A as a carryover moment. Half the value will be carried to A if it is fixed. Okay, so this is the modification. Let us see one example here. So this is an example. So analyze the continuous beam shown by kanis method. So you see there is span AB, which is of 3 meters, then BC 6 meters, CD 3 meters, DE, which is a cantilever portion, 2 meters, overhang. So this is a continuous beam with overhang. The span AB has an eccentric point load, 60 kilonewton. BC has got UDL, CD has got central point load, DE has got a point load at free end. Okay. Right. So step one will follow fixed end moments. So span AB, fix it, and write fixed end moments like PAB square by L square is the formula. And similarly, PAB square by L square is the formula. So these are all the values that are being practiced very well from the previous sessions. So even BC WL square by 12, these are the values. And for CD, fixed end moments, PL by 8 because central point load. So these are the values. Now you come to portion of cantilever, that is overhanging portion. The DE moment D because of that cantilever portion is 20 into 2. So minus 40 is the cantilever moment. Now the moments shall be modified. So what shall I do? You see, moment at D is plus 15 minus 40. So total, there is a balance of 30. I mean 25 is the balance, minus 25 is the balance. So to make it 0, we will be applying plus 25 to MFDC. So MFDC is only 15. So you have to make this 40 so that it is minus 40. So these two, if you add, it becomes 0. So to make 15 to 40, you have to add plus 25 so that it becomes 40. So MD, sigma MD is equal to 0. So you have added plus 25, rather you have applied plus 25 at D. So far end, that means to see how much you shall carry, half the value. So that means plus 12.5. What is already there? There is minus 15 already there. This is the moment. So minus 15 plus 12.5. Finally, you are getting minus 2.5. So now, instead of this value, we use this one. Instead of this one, we use this one. So these are modified moments. Remaining values will be unaltered, no change. Okay, so this is step one. Let's go to step two. Rotation factors finding is very similar to the earlier sessions. So you make columns like joint name, member name, stiffness value, total stiffness at the joint, then rotation factor. Then joint B has got two members, BA, BC, and where if you say A is the far end which is fixed, so 4EI by L we are using, and C is continuous, it's like fixed support, it's 4EI by L again. Similarly, joint C, CB, B is continuous, so 4EI by L, CD. Now D is a like you have to treat that as end hinge. So that's why it is 3EI by L. So CD, where D looks continuous, but you can see D looks continuous, but you have to treat this as end hinge. So modify the stiffness value. Okay. So this is a change. Right. Then DC is again where C is continuous. So we use 4EI by L, and DE 0 because it is cantilever. There won't be any stiffness for this because the end E is free. Okay, right. So once you take the formula minus 1 by 2 times K by sigma K, you get all these rotation factors. Okay, right. So this is how we make the rotation factor table. Then we prepare the beam for the rotation contribution calculation. So how you prepare it? By drawing the beam by replacing the joints with the boxes so that to accommodate the rotation factor values as well as the sum of fixed end moments at that joint. Okay, and the end hinge, if you see, I mean cantilever portion shall be maintained as it is. Right, now you write all these fixed end moments which are found from the step 1, and you see this is modified value, and then cantilever moment minus 40. Okay, and the free end is 0. Now these are all rotation factors, minus 0.33, minus 0.17, minus 0.2, minus 0.3, which are found there in the previous table. Then take the total moment at P. 26.67 minus 60 will be minus 33.33. 60 minus 2.5, 57.5. Okay, so these are fixed end moments. Now, to calculate rotation contribution at joint B, for member BA, use minus 0.33 rotation factor, sum of fixed end moments plus far end rotation contributions. So A rotation contribution is 0. C there will be a value, but it is not available in the first cycle, so we take 0. And this is the value. So this value is M dash BA, which means uh, moment developed at B in AB because of rotation of the joints. Next, BC. Just change the factor, remaining all are same. The sum of fixed end moment same, foreign contribution same. You get 5.67 is the M dash BC. Then coming to joint C, rotation factor minus 0.2, sum of fixed end moments 57.5, foreign contributions 5.67, 0. Then that comes to minus 12.63. Then the other member, m dash CD, change the factor, rotation factor, then within the braces it is same. So minus 18.95 is the m dash value. So these are all four uh, rotation contribution values. So we follow similar procedure for cycle 2 and we get these values. Okay, so foreign contributions shall be read with the latest values. Okay, so you see 0 minus 12.63. Similarly for giant C, 7.81, 0. So once you find these values, you shall immediately update here, so that if you don't update this 7.81 here, we will be taking this value as the far end contribution. That means that is a mistake that you are going to commit. Okay, so once you find 7.81 value, if you update it here, if you write it here, then we will be taking that as far end rotation contribution for the next joint calculation. Okay, similarly third cycle values, then fourth cycle values are almost stabilized. You can see 15.31, 15.32. So there is a difference of 0.01. Difference is 0, difference is 0, difference is almost 0. So now we use these values, fourth cycle values, for end moment calculation. Now you can see what will be the changes that will happen for end moment calculation. So now you make columns of all the points, nodes available in the beam, given beam, C, D, E. So where first row will be fixed end moments, we write all these moments and you shall see that these are modified values posted here. Then 2 times near end rotation contribution. That means if it is A, rotation contribution into 2. If it is B, 15.32 into 2. Again, B in BC, 7.89 into 2. This value. Minus 13.08 into 2 is this value. Minus 19.62 into 2 is this value. 2 times 0, and this side it is also 0, and these are all zeros. Rotation contributions will not be there for cantilever. Similarly, far end rotation contribution. So B to A and A to B, you shall interchange. Similarly, these two will be interchanged. And now from C to D, this one. Okay, so 19.62 will not be taken to D. That means that is 0. So rotation contribution from C to D will be 0 because D is hinge. Okay, because though it looks continuous, we will treat this as end hinge, as I told earlier. Right. Then once you write all those values, then add all these values to get final end moments. Okay. So likewise, joint B has got 57.31 minus 57.3, and joint C has got 41.73 and 41.74. So sum of moments at B shall be 0, sum of moment at C shall be 0, and at D shall be 0. So these are all the joint equilibriums that are to be satisfied. Okay, so this is how we solve the continuous beam with overhang. So possible changes that are to be once again to briefly to let you know that moments shall be modified for the portion which is adjoining to the cantilever, so that MFCD and MFDC values will be modified. Then step 2, rotation factors will have to take care of that when the adjoining support to the cantilever shall be treated as the simple end, so that the stiffness value will become only 3 by L instead of 4 by L. Then the process of finding rotation contribution will not change, only the final end moment calculation. This that is to be noted that from C to D foreign rotation contribution will not be there, 0. Okay, right. So next session we'll take up this continuous beam with sinking of supports.